Now, we want to work on the quantum mechanical model of the atom. The quantum mechanical model of the atom takes into account that electrons behave not just like particles, but like waves. It also takes into account the various forces that act upon electrons in an atom, and it takes into account aspects of the Heisenberg uncertainty principle. So, without further ado, let's meet our first term associated with the quantum mechanical model of the atom, and that's atomic orbitals. Atomic orbitals. In the Bohr model of the atom, we referred to electrons having orbits. That's a type of gum now as far as we're concerned. Electrons exist instead in atomic orbitals. An atomic orbital is a region of space with a definite shape where there is a high probability of finding an electron. I like to define atomic orbitals as where electrons like to hang out. We're going to describe atomic orbitals using 3 quantum numbers. Each of these quantum numbers is representative of a different property of the orbital. We've already met one of these quantum numbers. The atomic orbital concept is derived from what's known as Schrödinger's equation. Schrödinger's equation is an equation that takes into account the wave-like properties of atoms and the wave-like properties of electrons and the forces acting upon them. When the wave equation is solved, it produces what's known as a wave function. And trust me, if you take PChem, you'll understand why the wave equation is represented by a pitchfork, because it's pure evil. When the wave equation is squared, the square of that wave function, this is your wave function. When your wave function is squared, that defines your atomic orbital, or defines the probable location of an electron. This is one of those things where it's kind of like in terms of what you're going to know for an exam about the square of the wave equation. The square of the wave function and the wave function and the wave equation. I've got it summarized right here for you, but there's nothing really you can do with it. Until you've had through Calc 4, you can't really do a whole lot mathematically with the wave function or the wave equation. But for those of you who are continuing on in chemistry or physics, you will actually get to do them. Right now, I think we're just making some P-chemist happy by introducing them to you at this point. Your wave function is characterized, let's go through this. Your wave equation is solved, and when the wave equation is solved, you get a wave function. When you square that wave function, you get the probable region around the nucleus where you are likely to find an electron. This wave function here can be described using 4 quantum numbers. These quantum numbers are your principal quantum number, your angular momentum quantum number, your magnetic quantum number, and your spin quantum number. Each of them is represented by a unique symbol, and that symbology is used nearly universally by anybody who wishes to talk about these quantum numbers. I will warn you in advance, I think this is perhaps the most memorization intensive part of the semester if you've not had any of this before. Key to understanding what we're about to do and key to getting through what we're about to do is the ability to link these 4 quantum numbers to what they represent in terms of the placement of electrons. Let's take a look at these quantum numbers one at a time. First, let's take a look at the principal quantum number. We've already met the principal quantum number. The principal quantum number is represented by the lowercase letter n. Hey, in case you're wondering, yes, that n. Remember, we just got through talking about Heisenberg and Bohr and how we had a constant divided by n squared. That n squared we were dividing by is the principal quantum number. Therefore, you already know that a principal quantum number has to be a positive integer. You also know that the principal quantum number is another way of talking about the energy an electron has. We often refer to that principal quantum number as the energy level of an electron. We also know from the work of Bohr and Heisenberg, which we've already discussed, that this principal quantum number and that value of n tells us not just the energy of the electron, but it has something to do with the electron's probable distance from the nucleus. And here I am writing all over my notes, which are already telling me that. It describes not just the energy level and the distance from the nucleus, which we need to add in there, but it also tells us something about the size of an orbital. The principal quantum number describes the size of an orbital. If you think about your atom, and we apply the Bohr model, so to speak, to our quantum mechanical concept here, we already know you've got your first energy level, your second energy level, your third energy level. See, I told you I can't make threes. Your fourth energy level, and your fifth energy level. As you go away from the nucleus, and as your principal quantum number increases, in order for your new energy levels to fit around your old ones, they have to get larger. It's like Russian nesting dolls, right? The one inside is really small, and then each one around that goes around it is larger and larger by necessity. The same way for orbitals. As their principal quantum number increases, they get farther away from the nucleus, and therefore their size has to increase. All right, let's see. We've already covered that your principal quantum number can only have values of n equals 1, 2, 3, 4, 5, 6, 7, positive integers. The number of electrons that can have the same principal quantum number is 2n squared. When we talk about principal quantum numbers, let me say it emphatically, we're talking about the energy level in which an electron resides. Consider principal quantum number to be a synonym for energy level. The number of electrons you can have in an energy level is equal to 2n squared. So if you're in the first energy level, you can have 2 electrons. If you're in the third energy level, you can have 18 electrons. If you're in the fifth energy level, you can have 50 electrons. Let's see, I think we've discussed these previously, but let's go through them again real quickly. As the value of n increases, the energy an electron can possess increases, and we had a long discussion about that in our previous lecture. Not only that, but as n increases, the distance from the nucleus increases, and we talked about that as well. And we'll add one more. Size increases, the size of the orbital. So your principal quantum number can tell you quite a bit. Size, distance from the nucleus, and the energy of the orbital. Why don't you write down angel? Write down angel. A-N-G-E-L. Angel. One of the wonderful things about quantum mechanics is we like to double or triple name things when it comes to quantum mechanics. When we have a principal quantum number of 1, we can say we're in the first energy level, or we can say we're in the K energy level. All your energy levels are also named using capital letters. The capital letters start with K equal 1 and then proceed alphabetically. So instead of talking about the second energy level, I could talk about the capital L energy level. Or instead of talking about the third energy level, I could talk about the capital M energy level. This notation I have seen used, usually in papers by p-chemists. I don't see these capital letter notation used as often in other fields of chemistry. But they are out there and you need to be aware of them, particularly if you're considering a career in chemistry or biology. One way to discuss quantum numbers and help ourselves wrap our brain around them is to use what's known as orbital diagrams. And what you're looking at here is indeed an orbital diagram. And in this orbital diagram, we have energy increasing in this direction. And you'll remember from our previous discussion of energy levels, as the energy of an electron increases, so does the distance from the nucleus, on average. The average distance from the nucleus, or the likely distance from the nucleus. Also, looking at this diagram, you see your energy levels, and then you see that your energy levels appear to be broken up. You see your 1 here with an S next to it. You see your 2 here with an X next to it, and a 2 with a P next to it. 3, 3P, 3D, 4S, 4P, 4D, 4F. They are giving us hints that we are going to now subdivide our energy levels into smaller pieces. We're going to take our energy levels, or our principal quantum numbers, and divide our energy levels into sublevels. These sublevels are going to be represented by our next quantum number. And now our second quantum number. Our second quantum number is our angular momentum quantum number. And our angular momentum quantum number is the one that tells, if we're to relate it sort of to the Bohr model, we'd say that our angular momentum quantum number describes the sublevel in which the orbital resides. We have energy levels, and we break those energy levels down into sublevels using our angular momentum quantum number. The angular momentum quantum number is represented by a cursive letter L. That's supposed to be a cursive letter L there. What your angular momentum quantum number does is it does something very important. It defines the three-dimensional shape of your orbital. You'll often hear the angular momentum quantum number, in addition to being called a sublevel, you'll hear it called a subshell. Your angular momentum quantum number is described numerically, just like your principal quantum number. Principal quantum numbers can have values of 1, 2, 3, 4, positive integers. The value of your angular momentum quantum number is also an integer, but they start with 0. They can have values of 0 to n minus 1. You can tell that your angular momentum quantum number represents a subdivision of n of your principal quantum number because its value is dependent on the value of the principal quantum number. For example, if you have a principal quantum number of 1, then you can only have one value for your angular momentum quantum number, 0. If you have a principal quantum number of 2, then your angular momentum quantum number can have values of 0 or 1. If you're in your third energy level, then your angular momentum quantum number can have values of 0, 1, or 2. If you're in your fourth energy level, then your angular momentum quantum number can have values of 0, 1, 2, or 3. Notice something. The number of possible values of L is equal to n. For example, when n is 1, there's only one possible value for our angular momentum quantum number. When n equals 2, there are 2 possible values. When n equals 3, there are 3 possible values. When n equals 4, there are 4 possible values. We can use this to draw a conclusion in the real world. In the real world, we would say, not the real world, that's a bad term. In our concrete way of thinking about it, in our Bohr model way of thinking about it, we could say the number of sublevels or subshells in an energy level is equal to the number of the energy level. If you've had chemistry before, then you also know that the angular momentum quantum numbers can also be represented by letters. Unlike energy levels, the angular momentum quantum number is most commonly talked about in terms of its letters. When the angular momentum quantum number has a value of 0, it's referred to as S. When the angular momentum quantum number is 1, we refer to it as a P, 2 a D, 3 an F. You are responsible for knowing that an angular momentum quantum number of 0 corresponds to S, 1 to P, 2 to D, 3 to F, and the rest in alphabetical order. So if L equals 4, we would also refer to that as a G. If L equals 5, we'd refer to that as an H. However, filled in nature, we only find F, 0 through F, or S, P, D, and F. Let's tie this together a little bit. So we have our principal quantum number, and our principal quantum number defines our energy level. Each energy level is broken down into sublevels. The sublevels are represented by the angular momentum quantum number, and the angular momentum quantum number tells us the shape of the orbital. More on that later. If we're in the first energy level, then the only possible value for L is 0. So we would say that our sublevels would be 1s. If our principal quantum number is 2, then our angular momentum quantum number could be 0 or 1. So we would have two sublevels. We would have a 2s and we would have a 2p. If we have a principal quantum number of 3, then we'd have an angular momentum quantum number of 0, 1, and 2. So we would have a 3s, a 3p, and a 3d. Notice how we call the first sublevel of any of our energy levels S. We call the second sublevel of any of our energy levels P, and the third D. If we were to keep this party going, our fourth energy level, principal quantum number 4, could have angular momentum numbers of 0, 1, 2, 3. So we would have a 4s, a 4p, a 4d, and a 4f. So now we've met our second quantum number. If we return to our orbital diagram, we can see very clearly that we have our first energy level, and our first energy level has one sublevel. We have our second energy level with two sublevels, 2s and 2p. We have our third energy level, 3s, 3p, 3d. We have our fourth energy level, 4s, 4p, 4d, and 4f. So we can see that each energy level is divided into sublevels. It turns out, however, that this energy diagram creates a little bit of an illusion, because if we look at this energy diagram, it appears that all of our sublevels have equal energy. In reality, there's a difference in energy between the sublevels, just like there is between the energy levels. Let's look at a corrected version of our orbital diagram over here, where we can see that in every single where if we look at the first energy level, we only have the s, so we can't really talk about energy differences in sublevels there. But if we look at the second energy level, we can see that the s sublevel has less energy than the 2p. If we look at the third energy level, we can see that the 3s has less energy than the 3p, which has less energy than the 3d. We look at the 4s, we see it has less energy than the 4p, which has less energy than the 4d, which has less energy than the 4f. Also, and I'm just throwing this out there and we'll expound upon it more, look what happens if we draw a dotted line from our 4s. Doot, 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 doot. If I drew that straight with a ruler here, let me try to draw it straight, you'll notice that the energy of that 4s is just lower than the energy of the 3d. That's going to be important here in a few minutes. But for now, all you need to realize is that sublevels have different energies. And if we did it from a quantum number perspective, the energy of the sublevel increases from 0 to 4, or from S to G. So energy increases that direction, and if energy is increasing, what does that also mean about probable distance from the nucleus? that also means our probable distance from the nucleus is also increasing. This just summarizes some of the things we've just talked about in regards to sublevels, or our angular momentum quantum number. In any energy level, the S sublevel is always going to have the lowest energy. The S sublevel is followed by the S, P, D, and F sublevels in order of increasing energy. The higher sublevels are possible, but only S, P, D, and F sublevels are found to hold electrons in the atoms we know about today. Your first energy level has only an S sublevel, your second has an S and a P, your third an S, P, D, and F, and fourth S, P, D, and F. One thing that I want to make clear of, I think the energy diagram shows that correctly. Inside an atom, there's more than one S, right? There's a 1s, a 2s, a 3s, and a 4s. Every single energy level has an S, right? There's not just one S for the whole atom. For some reason, people get confused by that. I'm just making sure that you realize that. There's more than one P, right? There's a 2P, a 3P, and a 4P. Just like there's more than one Pikachu card out there, right? There's multiple Pikachu cards out there. Everybody has one if you've collected Pokemon long enough. Guess what my son's into at the moment. But at any rate, moving on. Graphically, again, I'm driving home this point. Notice in our orbital diagram here, there are lots of S's, right? There's a 1s, a 2s, a 3s, and a 4s. There's lots of P's, a 2P, 3P, 4P, 3D, 4D, 4F, and there's a 5F. So there's more than one of every sublevel. It's just inside an energy level, there's only one S and one P. Inside the third energy level, there's only one S and one P. But inside the atom, there's several. And you can see that with this energy diagram. Why don't you write down Cordelia? Write down Cordelia. I hope you're writing down Cordelia. All right. The angular momentum quantum number tells you more about the energy of the electron. It tells you also the shape of the orbital. And this is where Bohr got it dramatically wrong. Remember, Bohr had those boring circles. Boo, hiss. The shape of an orbital in reality is much more complex and much more interesting. When you square the wave function, you get a graph. And that graph is really a pointillism graph almost. If we were to look at these pictures that you're seeing here, what you'd see is that really they're a series of pointillism things almost, a collection of little dots. The square of this wave function produces these shapes. The square of this wave function tells you the probable location of where an electron is likely to be. An electron is likely to be somewhere along the surface of one of these shapes. Each angular momentum quantum, the angular momentum quantum number tells you which one of these shapes an electron's orbital will take. If your angular momentum quantum number is 0, in other words, you're in an S sublevel, then the orbital will be a sphere. That's three-dimensional. Then your orbital will be a sphere. If your angular momentum quantum number is equal to 1, meaning you're in the P sublevel, your orbitals will look like two ice cream cones. If we blow these up, and I'm getting rid of this guy for a reason, we'll talk about that one later on, but if we looked at these P orbitals right here, you'd see you have an ice cream cone here, and an ice cream cone there. It's hard to tell from these pictures, but what do you think is right there at the origin of your axis? Right there is your nucleus. The probability of an electron being in the nucleus is 0. So your ice cream cones don't really touch. Right? That's the shape of your p orbital. Right? They're not touching because into the center is a nucleus and the probability of an electron being there is 0. So those are your p orbitals, and you're responsible for knowing these shapes. If you were in my face-to-face class, one of my classic multiple choice questions is to either ask you, well, not a multiple choice, sometimes it's open response, is to ask you to sketch the shape of a p orbital, or if your angular momentum quantum number equals 0, sketch the shape of an orbital. If your angular momentum quantum number is equal to 2, in other words, you're in a d orbital, your shapes are clover-leafed. You actually have more than one shape here. First of all, ignore this shape down here. Focus on this one, this one, this one, this one, and this one. You'll notice that your possible shapes for your d sublevel orbitals are clover-leafs. You have 4 ice cream cones. Once again, those ice cream cones don't touch in the middle. Where that nucleus is, they don't touch. So you have 4 ice cream cones, and then you have the orbital I like to call the Homer Simpson special. Why? Because, donuts. You have 2 ice cream cones, and then you have a donut going around the center there. This picture's not the best one. If I were to do my own artwork, you'd have a donut hollow there because the nucleus is right there. Then you'd have an ice cream cone sticking out below, and an ice cream cone sticking out above. And apparently I am having trouble with above and below today, so even though I can talk about quantum mechanics, I need to go back to kindergarten. So you have 2 possible shapes, really, when you're talking about your d orbitals, the Homer Simpson special or your 4-leaf lucky clover. And those are the shapes of the orbitals that you're responsible for knowing. So your angular momentum quantum number tells you the shape of the orbital and some more information about the energy of the electron in the orbital. All right, quick review. We've got our principal quantum number that tells us our energy level, tells us the size of the orbital, and tells us relative distance from the nucleus. Provides all that information about our orbitals. Then we have our angular momentum quantum number, and that tells us the shape of the orbital, and it tells us a little bit more about the energy. We also equate our principal quantum number with the energy level, and we refer to the angular momentum quantum number as the sublevel. Now, inside every sublevel is divided into orbitals. We identify a specific orbital using the magnetic quantum number.
Magnetic quantum number.
That's right, magnetic quantum number. So what we now have is, by using these 3 quantum numbers, the principal quantum number, the angular momentum quantum number, and our magnetic quantum number, a set of 3 numbers that can be used to identify an orbital. So if we have these 3 numbers, we're talking about one orbital. Now, what information does this magnetic quantum number provide us? If it's talking about a specific orbital, how do we know what specific orbitals it's talking about? Moreover, what values can those magnetic quantum numbers have? The easiest way to tell tell what the magnetic quantum number is telling us is to say that the magnetic quantum number says the orbitals orientation in three-dimensional space. For example, first of all, let's look at our rule real quickly about the values that m sub l could have. M sub l, notice how that is subscript L, and L is our angular momentum quantum number. That's telling you that the values of the magnetic quantum number depend on the values of the angular momentum quantum number. Your magnetic quantum number can have values of negative L to positive L. And after I finish this lecture, I really think the only thing I'm missing is a can of tomato sauce to make this lecture into alphabet soup. But m sub l can have values of negative L to positive L. So if L equals 0, then what's the only possible value for m sub l? 0. And we said if L is 0, then we're in the S sublevel, which means that we have a spherical shape or a spherical orbital. How many ways can you twist or turn a sphere in space? You can only twist or turn a sphere in space one way. So there's only one possible orientation for a spherical orbital, which your S sublevels orbitals are. Your S sublevels are all spheres, so there's only one way you can orient them in three-dimensional space. Therefore, that means that your S sublevel can have only one orbital. And that orbital will be the m sub l equals 0 orbital. Let's look at the more interesting case scenario here. Let's go with L equals 1.
L equals 1?
L equals 1.
Maybe L can equal 1?
L can equal 1. L can have any value from 0 to n minus 1.
I didn't know that.
Now you do. So,
Because L is my favorite letter.
I understand L is your favorite letter because what's your name?
Yeah.
What's your name?
Ian Curry.
That's right. And it begins with the letter L. But I digress. L, when L equals 1, that means we're in the P sublevel.
Sublevel.
And when we're in the P sublevel, our orbitals have that double ice cream cone shape that we talk about.
Ice cream!
Now, if L equals 1, then m sub l is going to have values of negative L to positive L. So it will have values of negative 1, 0, and positive 1. Now, let's think about our double ice cream cone shape here. Let me improve my artwork a little. A double ice cream cone shape is essentially a straight line. How many ways can you turn a straight line in three-dimensional space? You can turn it 3 ways, right? You can lie it along the x-axis, you can lie it along the y-axis, or you can lie it along the z-axis. So there are 3 ways you can put that double ice cream cone shape in three-dimensional space. That's why you have 3 values of m sub l. So that means that you have, because you have 3 values of m sub l, that means you have 3 orbitals in the P sublevel. So see are you beginning to see the correlation? Your m sub l values tell you the number of orbitals, and each one of these values represents a different orbital. Now things get really wild and crazy when we look at, let me clean things up here. things get really wild and crazy when we look at our D's. We have our angular quantum momentum number of 2, and that means we're in the D subshell. If L has a value of 2 and M sub L, our magnetic quantum number can have values of -2, -1, 0, 1, and 2, or 5 values. Since M sub L can have 5 values, that means our D sublevel can have 5 orbitals. Each one of those orbitals is going to have a different orientation in three-dimensional space. Now remember, when L equals 2, the shape is that 4-leaf clover, or those 4 ice cream cones. These 4 ice cream cones can be arranged 4 different ways in three-dimensional space. You can put them so that they lie in the plane of XY. You can put them so they lie in the plane of YZ. You can put them so that they lie in the plane of X and Z. Or you can put them so that they lie in what's known as x squared minus y squared, which is kind of along those axes right there. And then you have the Homer Simpson special, right? The donut with the ice cream cone through it. So you have 5 d orbitals, each one of those orbitals having a different magnetic quantum number. So our magnetic quantum number tells us the orientation in three-dimensional space of our shape. The number of values of M sub L tells us the number of orbitals that exist in a sublevel. To summarize, the magnetic quantum number defines the spatial orientation of the orbital. There are 2L plus 1 values of M sub L for every value of L. I should put that in there for and M sub L can have any integral value from -L to +L. And then we go through those examples we talked about. And more importantly, our magnetic quantum number. Matter of fact, let me say this. Let me put it this way. Using the principal quantum number, the angular momentum quantum number, and your magnetic quantum number, these 3 numbers together identify a specific orbital. For example, if I told you you had the quantum numbers 2, 1, 0, you would have an orbital in the second energy level. Since oh, by the way, quantum numbers are always listed in the order of N, L, M sub L. And L equals 1, so that means you have the P subshell. M sub L is an orbital. M sub L equals 0 is an orbital, and if you look at your little chart, -1, 0, 1 goes X, Y, Z, so it would be py. It would be the 2py orbital would have this set of quantum numbers. So by giving 3 quantum numbers, we can identify a specific orbital. More importantly, I think, for you to take away from this, because of a more practical standpoint, especially for those of you going into the soft sciences like biology, couldn't resist, is the number of orbitals on a subshell. If you're in the S subshell, you have 1 orbital. Why? Because L is equal to 0, and 2 times 0 plus 1 is 1. So you have 1 orbital. If you're in the P subshell, you have 3 orbitals. Why? Because L equals 1. 2 times 1 plus 1 is 3. If you're in the D subshell, you have 5 orbitals. If you like patterns, you may also be noticing at this point that it's a +2 pattern. So if you're in the F, you're going to have 7. That's an F. Wow. Try that again. F. There we are. F, you have 7. Why? L equals 3. 2 times 3 plus 1 is 7. You need to remember that. If I asked you how many G would be 9. So you need to remember those. Here is a very nice study chart. If I were you, I would print this chart off and make sure that I had it with me when I was doing my homework and when I was studying, and I guess since it's online, you might even want to have it when you have an exam. How this chart is arranged, if this is your principal quantum number, this is your angular momentum quantum number. This is your magnetic quantum number. This would be the orbital notation, right? And this corresponds to your n value and your L value. Then you have the number of orbitals, and that's your number of m sub L values. And this is in the subshell. This is the number of orbitals in the energy level. They say shell or think energy level. Although really I should be saying energy shell, because energy shell is the Schrodinger terminology, where energy level is the Bohr model. I'm kind of stuck on that because I was taught the boring way. One thing I promise never to be. Long-winded maybe, but never boring. You can see here, well, I won't bother to go through everything. Principal energy level 2. You can have 2 subshells, an S and a P. Your S has 1, your 2P has 3. Altogether, in your second energy level, you have 4 orbitals. And the journey continues. The only thing I might add, if I were making this chart, is I might add a number of electrons over here. Remember, your number of electrons is 2n squared, so I'd have number of electrons in an orbital. Number of electrons in an energy level. And I'll refer to you to a previous overhead for that. We didn't cover the number of electrons in a subshell. Let's do that real quickly. If we're in the S subshell, your number of electrons is going to be double your number of orbitals. only 2 electrons can occupy an orbital. And we'll actually apply a fancy term to that and name it after some dead guy, but right now just take it for a statement of fact that only 2 electrons can occupy an orbital. So if I'm in my s subshell and I have 1 orbital, then my number of electrons that can be in the s subshell is 2. If I'm in a p subshell, I can have 3 orbitals and a total of 6 electrons. If I'm in a D, I have 5 orbitals, so I can have 10 electrons. If I'm in the F, I can have 7 orbitals or 14 electrons. And you're responsible for knowing that. Identify the shell and subshell of an orbital with the quantum numbers n equals 3, L equals 1, and M sub L equals 1. That's my energy level. Boom! Or my energy shell. 3. L equals 1 means I have a P. 0 is S. And 1, traditionally that would be the PY if we were going to be doing it that way. There you go. Chemistry is easy, life is hard. Seriously, I'm only semi-joking when I said it sounds like I'm making alphabet soup here. If you've never had this material before, then you have had a lot thrown at you. And a lot of you are confused. What I would do is I'd start the Mastering Chemistry homework. If you begin to struggle with it, or if you don't think you can figure it out, stop and actually go on to the next couple lectures. I know that sounds silly to go forward when you don't understand the past, but this is one of those things where I think it actually becomes easier if you see the concepts that flow from it. Matter of fact, you know what I'm going to do? I'm going to record a special lecture for you to listen to right after this before you do the homework. Chemistry is easy. Life is hard. Trust me on that one. Ooh, the gift that keeps on giving. Give all the possible combinations of the 3 quantum numbers for a 4p orbital. Well, if I'm in the 4p, if I have 4, that means n equals 4. If I have a p, that means L is equal to 1. And now my M sub L values are dependent only on my L values. My principal quantum number doesn't matter in terms of my magnetic quantum number values. Only my values of L. So it can have negative L to positive L. So my possible sets of quantum numbers would be 4, 1, negative 1, 4, 1, 0, and 4, 1, 1. And now we're finally done with the lecture.